In this video, I'll be covering how to integrate using partial fraction decomposition. There's three main steps you take when integrating with this technique. The first step is to split the fraction. The second step is to solve for the constants, and the third step is to integrate your new problem. These first two steps are your partial fraction decomposition, and the last step is just integrating the new question. Alright, so here's a brief overview of how you can split your fractions. If you have a term with a singular x, for example, here's x plus 1, then you'll have a single constant over that term. If you have a quadratic term, for example, here we have x squared plus 2, then you'll have a term that's in the form of bx plus c over that term. And if you have a term squared, then you'll split the term into two different parts out like this. And I'll go into more detail on this in the examples. Alright, so our first example here is the integral of x squared minus 11 over x cubed plus x dx. So our first step is going to be to split the fraction. But in order to do that, we need to fully factor our denominator. So that our denominator can turn into x times x squared plus 1. Now we can do our split. X squared minus 11 over x times x squared plus 1 will equal a over x, because that's just a singular x term, plus bx plus c over x squared plus 1, because that is an x squared term. Now we need to solve for our three constants, a, b, and c. So we can start by multiplying each term in this equation by this denominator, x times x squared plus 1. So we'll be left with x squared minus 11 equals a times x squared plus 1 plus b x plus c times x. Now we need to solve for our constants. And the easiest one to solve for in this situation is a, because we can test when x is equal to 0. So let's substitute in 0 for all of our x values. This term here will simply become negative 11. This will all be 1 times a, which is just a. And like I said, this was all going to become 0. So now we know that a is equal to negative 11. Using that information, we can plug in negative 11 for a in this current equation. So rather than writing a here, let's write negative 11 times x squared minus plus 1 plus, and let's go ahead and distribute this x now. So that's bx squared plus cx. Now we can go ahead and distribute this negative 11. So let's rewrite this as negative 11 x squared minus 11 plus bx squared plus cx. These 11s will cancel on both sides, and we can bring this negative 11x squared term to the other side. So that'll become 12x squared equals bx squared plus cx. Now from here we need to use some logic. Since the left-hand side of this equation doesn't have any x term on its own, it only has x squared terms, we can figure out that c is just 0. And if c is 0, then this term goes away. And to match up these terms, b would just be 12. Again, since if there was an x term over here, for example like this, then we need to solve for whatever c was. But in this case, that doesn't exist. So now that we have our three constants, we can go ahead and plug them in this form. So let's rewrite our integral as a, which is negative 11 over x. Again, we're following this term. And now we know that b is 12, so we can do plus 12x over x squared plus 1 dx. This first part here is just negative 11 absolute value, ln absolute value of x, plus, now we need to do a simple u sub here, so we can set u equal to x squared plus 1, du will equal 2x, so this becomes the integral of 6 over u du. And so our final answer will become negative 11 ln absolute value of x plus 6 ln absolute value of x squared plus 1 plus c. And that is how you can use partial fraction decomposition to solve an integral. Alright, so the second example here might not initially look like a partial fraction question, but it will become one after we use a u sub. So we're going to start by setting u equal to tangent of x, and du will become secant squared x dx. We can now rewrite this as du over u squared plus 9u plus 20. So now we want to factor the bottom. And that will leave us with du over u plus 4 times u plus 5. So now this is starting to look like a partial fraction question. And we can say that 1 over u plus 4 times u plus 5 is equal to a over u plus 4 plus b over u plus 5. And now we've split the fraction. Now we need to solve for a and b. So we're going to multiply each term by the denominator. So 1 equals a times x plus 5 plus b times x plus 4. Let's start by solving for a, and to do that we need to get rid of this term by testing when x is equal to negative 4, because that will make this 0 and make that whole term go away. So x equals negative 4, 1 equals a times negative 4 plus 5, that's just 1, so that means that a is equal to 1. Now we need to solve for b. And to make this term equal to 0, we need to set x equal to negative 5. So when x is equal to negative 5, 1 is equal to b times negative 5 plus 4. And this is negative 1, which means that b is equal to negative 1. So now we can go ahead and rewrite our integral. So this will become the integral of a, which is 1 over u plus 4, plus, which in this case is minus because it's negative, 1 over u plus 5 du. So now this just become simple integral rules. So this is ln absolute value of u plus 4 minus ln absolute value of u plus 5 plus c. But we need to remember that originally we set u equal to tangent of x, so our final answer will have to substitute in for u. So our final answer is ln of tangent x plus 4 minus ln absolute value of tangent x plus 5 plus c. And that is another way that you can use partial fractions to solve an integral question.